Module 3, Lesson 4, Paths and Cycles. For this particular module, we will be covering the definition of paths, graph connectivity, the different types of cycle, which is the Hamiltonian path and Hamiltonian cycle, the Euler path and Euler cycle, and finally dealing with different graph puzzles. What is a path? A path basically is a sequence of edges that begins at the vertex of a graph and travels from vertex to vertex along the edges of your graph. As the path travels along its edges, it visits the vertices along its path, that is, the endpoints of this corresponding path. Numerous problems can be modeled with paths formed by traveling along the edges of a graph, such as determining whether the message can be sent between two computers or efficiently planning routes for mail delivery system. In graph theory, a path basically is a sequence of vertices such that it eventually starts from what you call a start vertex, and then it goes on to the next vertex in sequence until it reaches your end vertex. A path basically is a sequence of vertices. Therefore, a path length is the number of vertices traversed from your starting vertex U to your end vertex V, where n turns out to be a positive integer. In an undirected graph, it's basically denoted to be a sequence of vertices that are noted as E1 to En. When the graph is simple, the path is denoted to be a vertex sequence, and that path is considered to be a circuit if it begins and ends at the same vertex and has a corresponding length greater than 0. A path or a circuit is said to pass through the vertices and traverse the edges. Thus, the path is simple if it does not contain the same edge more than once. The path length for a directed graph is basically also denoted as the number of sequences of edges that you have traversed, or the number of vertices that you have traversed on your corresponding respective graph. This is one such example. Given the graph below, you have A, D, C, F, E is basically a path of length 4. DECA is not a path because E is not connected to your vertex C, while BCFEB is a circuit of length 4 because the vertex you started is also the vertex where you have ended, while ABEDAB is a path of length 5, but it is not a simple path. How many paths of length 4 are there from A to D on this given simple graph? There are exactly 8 paths of length 4 from A to D. By inspection, you have AB, ABD, you have AB, ACD, you have ABD, BD, you have ABDCD, you have ACABD, you have ACACD, you have ACDBD, and finally, you have ACDCD, which meant that you can go back and forth on these vertices in order to complete that path length of 4 until you reach your terminal vertex, which starts from vertex A to vertex D. How many available paths are there from A to B in this given directed path? There are 2 available paths from A to B. That is, if you go directly from A to B with a path length of 1, and if you go from A to D, then C, and then B with a path length of 3. Graph connectivity. By definition, an undirected graph is connected if there is a path between every pair of vertices, and an undirected graph that is not connected is called disconnected. We say that we disconnect a graph when we remove vertices or edges or both to produce a disconnected subgraph. This is one such example. G1 is basically a connected graph because there is a path between any pair of its vertices, as can be easily seen. However, G2 is not connected because there is no path between vertices A and F. On a given directed graph, it is strongly connected if there is a path from A to B and a path from B to A whenever A and B are vertices of your graph. Therefore, on a directed graph, your graph connectivity is considered to be weakly connected if there is a path between every two vertices in the underlying undirected graph, which is the undirected graph obtained by ignoring the directions of your corresponding edges of the directed graph. Given here on this example, graph G is a strongly connected graph because there is a path between any two vertices on your directed graph, or there is a path going from A to B, and there is also a path going from B to A, following the oriented edges given on your directed graph. Whereas if you look at graph G is a weakly connected graph. Likewise, graph H is also a weakly connected graph because if you remove all the orientations on both graphs, meaning removing all the directions only, and the graph remains connected, therefore, these particular graphs are considered to be weakly connected. A simple path. A path with no repeated vertices is simply called a simple path. And when you say a simple cycle, it is basically a cycle with no repeated vertices or edges aside from the necessary repetition of your start and end vertex. Note that the choice of your start vertex is usually arbitrary, meaning you can start anywhere on any vertex given on the graph. A path such that no graph edge connects two non-consecutive path vertices is called an induced path. One of the more familiar cycles and paths given was the one invented by Sir William Rowan Hamilton, which he devised in order to solve what you call the Icosian puzzle. An Icosian puzzle basically is a wooden dodecahedron whereby you end up with 12 regular pentagon faces and a corresponding peg at each vertex. The object of the puzzle was basically to start at any peg and traverse along the edges, visiting each of your corresponding pegs exactly once, traveling along the edges, and go back to your first peg or first vertex. This is an illustration of a dodecahedron. If we lay out the dodecahedron flat on a graph, it would then look like this, and your respective vertices are as follows. Therefore, in order to solve this Icosian puzzle, Sir Rowan Hamilton created what you call a Hamiltonian cycle. Starting from any arbitrary vertex, he traversed the edges of your corresponding graph, going through each vertex exactly once, and go back to your starting vertex with a corresponding solution like this. By definition, a Hamilton path is a simple path whereby graph G passes through every vertex exactly once, and a simple circuit is simply a graph G that contains a simple path whereby it passes through every vertex exactly once and go back to your starting vertex. A path basically under Hamilton path is simply denoted to be, again, a sequence of vertices. And the length of your path is still the number of edges that your path uses, counting multiple edges if you encounter them multiple times. This is one such example. Let's try to determine which of the following is a Hamilton circuit, or if not, a Hamilton path. Given the following graphs G1, G2, and G3. G1 is a Hamilton circuit. Shown here, you could traverse each vertex exactly once with an arbitrary start vertex at vertex A. You'd end up with A, B, C, D, E, and A. While graph G2 is not a Hamilton circuit, but does have a Hamilton path. since you can still traverse each vertex exactly once. Starting from vertex A, you have A, B, C, and D. Whereas graph G3 does not have a Hamilton circuit or a Hamilton path. This is an example of Hamilton cycle in a given directed graph. Note, you can traverse all the vertices starting from an arbitrary vertex, start vertex, let's say vertex A, going to vertex B, C, D, E, and F, and go back to vertex A. This is an example of a Hamilton path on a directed graph. Note that you can only traverse vertex A, vertex D, vertex C, and vertex B. However, you can't go back to your starting vertex, vertex A, but you manage to traverse each vertex exactly once. So, from this given example, which of the following is a Hamilton circuit, or if not, a Hamilton path? You have graph G. This is a Hamilton path. Graph H. This is a Hamilton path. And graph G3. This is a Hamilton circuit. Given another example for a directed graph, which of the following of these graphs is a Hamilton circuit, or if not, a Hamilton path? Looking at H3, this is not a Hamilton circuit, nor is this a Hamilton path. This graph, you end up with, this graph is a Hamilton path. What about this graph? This graph is a Hamilton path. In graph theory, the other very common cycle or circuit is known as the Euler circuit. This time, the Euler circuit was used to solve the famous 7 bridges of Königsberg problem in 1736. The town of Königsberg, which was in Prussia before, was subdivided into 4 sections by the branches of your Pregel River. People eventually wondered whether it's possible to follow a path that crosses each bridge exactly once and return to your starting point. This is the graph layout for your corresponding 7 bridges of Königsberg. Each edge on this particular graph represents one bridge, connecting the different parts of your Königsberg city. Due to this, Euler managed to solve this given problem by defining what an Euler circuit is. A graph is considered to have an Euler circuit if it contains every edge of graph G. An Euler path is said to be a simple path containing every edge of graph G. Simply stated, an Euler path is a path in a graph which visits each edge exactly once. Similarly, the Euler cycle or Euler circuit is an Euler path which starts at a given vertex and visits every edge exactly once and go back to your starting vertex. As seen from the definition, you may go back and forth on the different vertices in order to cover each edge and traverse it exactly once. Which of the following graphs G1, G2, G3 has an Euler circuit? Of those that do not, which has an Euler path? G1 has an Euler circuit, which is denoted to be A, E, C, D, E, B, and A. Notice we went back and forth on vertex E. So this is possible as long as you cover each edge exactly once. Note, graph G3 is an Euler path, provided as A, C, D, E, B, D, A, and B. Whereas by inspection, graph G2 is does not contain an Euler path, nor does it contain an Euler circuit. Let's try to evaluate this example. This is an example of a corresponding directed graph, which is an Euler circuit. Note that you could traverse each edge exactly once by following the directed edges, noted to be starting from, let's say, an arbitrary vertex A, then go to G, and then C, and then B, and then go back to G, and then E, and then D, and then go to F, and finally back to A. This is an example of an Eulerian path on a given directed graph. You could start at vertex C, go to A, go to B, go back to C, and then D, and then finally end at B. You manage to cover each edge exactly once, but you fail to go back to your starting vertex, vertex C. Let's try to evaluate this example. Which of the following directed graphs on G1, G2, G3 has an Euler circuit? Of those that do not, which has an Euler path? Note, graph G1 is an Euler path. Graph G2 is an Euler path, while graph G3 is not an Euler path, nor is it an Euler cycle. On this next example, given the following directed graphs, which directed graphs has Euler circuit? Of those that do not, which has an Euler path? This particular graph contains, it does not contain any Euler path nor an Euler circuit. What about this graph? This graph contains an Euler path. What about this graph? This graph does not contain an Euler path, nor does it contain an Euler circuit. And then let's try to evaluate a few problems and try to solve this on your own. Given here are four coins that are initially on circles W, X, Y, and Z. And then the challenge is to slide along the coins on the edges so that your corresponding coins will rest at positions A, B, C, and D. However, whenever you slide coins, coins are not allowed to be adjacent to each other at any time. Meaning, if I slide the coin from the position Y to position V, I cannot slide the coin at position W, nor can I slide the coin Y to position V because that will make it adjacent to my W. Therefore, how many moves will it take to evaluate then and place your coins in the position A, B, C, and D? This is another puzzle. You are asked to write down the letters of the alphabet sequentially from A all the way to the last letter Z. However, you can only place respective letters on adjacent positions of your previous letter. Given here is the initial position of your letter A, which is found in box 2. Therefore, the only other position for B would be box 1, box 1, box 3, or box 11. This line makes box 2 and box 11 adjacent. Therefore, boxes that are connected by line are considered to be adjacent. So if you selected one of this corresponding position to be letter B, for example, you've selected position 3 to be letter B, the only other position for your letter C would fall in box 4. Since box 3 is only adjacent to box 4, and it's denoted that on box 6, you should end with the letter C. Therefore, where should the other letters fall into place? This ends Module 3, Lesson 4.